Data is the new oil, and machine learning is the refinery that extracts its value. But extraction engines need to be both powerful and efficient. Enter TensorFlow, a library that turns Python into a machine learning powerhouse. Powered by both high-level APIs and the raw core for tinkering, TensorFlow has something for everyone. That includes you. TensorFlow is an open-source machine learning framework from Google. Unlike their search algorithm, this one they chose to share with humanity. The name is quite literal. Data flows through computational graphs in the form of tensors. Perhaps you are familiar with vectors, one-dimensional arrays of numbers, or matrices, two-dimensional grids of numbers. Tensors generalize this concept to any number of dimensions. Observe the pattern. A scalar is a single number, zero-dimensional. A vector is an array of numbers, one-dimensional. A matrix is a grid of numbers, two-dimensional. And a tensor is simply an n-dimensional box of numbers. The concept is quite computable. Each operation in TensorFlow transforms these tensors through nodes in a computational graph. Addition, multiplication, neural network layers. The tensors flow through each transformation, hence the name. While neural networks are TensorFlow's primary application, it is not constrained to a single algorithm class. Other models include support vector machines, decision trees, and random forests. The framework distributes computations across multiple processing units: CPU, Central Processing Unit; GPU, Graphics Processing Unit; TPU, Tensor Processing Unit. For those who prefer not to construct neural architectures from fundamental components, TensorFlow provides the Keras API. Keras manages implementation details while you focus on model architecture. Today we shall explore the manipulation of tensors and construction of models using this framework. First, we import TensorFlow. The conventional alias is TF. TensorFlow includes two useful methods for creating tensors: constant and variable. If you do not need to change the values, use constant. If you do need a tensor that is mutable, in other words, changeable, use the variable method. We will seize the opportunity to conserve memory and create immutable tensors using the constant method. Let us convert lists of data into tensors. A list becomes a vector, a one-dimensional tensor. A list of lists becomes a matrix, two-dimensional. A list of lists. Do you comprehend the pattern? Let us print the shape attribute for each tensor so we can inspect the dimensional properties. Run. For each shape, the length, or number of numbers, tells you the tensor dimension. Each specific number is the length in that dimension. Note the syntax. The first shape has one number, indicating a one-dimensional tensor, also known as a vector. The specific number, 4, tells us the vector has 4 elements. Moving on. 4, 3 indicates a two-dimensional tensor, or matrix, with 4 rows and 3 columns. 2, 2, 2 signifies, well, perhaps we should proceed to other topics before we exceed available dimensions. TensorFlow provides additional tensor initialization functions. The zeros function generates a tensor populated with zeros. The ones function produces a tensor with, wait for it, ones. And the random module includes a normal function for creating a tensor pre-populated with random numbers from a Gaussian distribution. Before we move on, let us demonstrate a case where TensorFlow will refuse to create a tensor. Unlike Python lists, TensorFlow requires tensors to have consistent dimensions across all axes. Let us attempt to create a two-dimensional tensor where the rows have different lengths. This raises an error because the rows are not of equal length. TensorFlow enforces this constraint to ensure tensors are well-defined and suitable for efficient computation. While this may feel restrictive at first, it is critical for consistency in mathematical operations. Time for more restrictive rules. In TensorFlow, every element in a tensor must share the same data type. This requirement ensures efficient computation. It is also wise to use the smallest data type that can accurately represent your data. This conserves memory and improves performance. Let us explore TensorFlow's type system with a demonstration. Integer tensors are used for discrete values, like counts or indices. TensorFlow supports a variety of integer types, including 8, 16, 32, and 64-bit integers. Float tensors represent continuous numerical values. TensorFlow supports 16, 32, and 64-bit floats, with 32-bit being the default for most computations. Boolean tensors hold logical true or false values, making them ideal for conditional operations. Finally, complex tensors represent numbers with real and imaginary components. TensorFlow supports complex 64 and complex 128, where the real and imaginary parts are stored as 32-bit or 64-bit floats, respectively. Choosing the right data type is not just about correctness, it is about optimization. Smaller types save memory and computation time, especially when working with large datasets or models. Are your tensors flowing in style? Time to investigate our Python merge. It is designed to keep you looking sharp in every dimension. Whether you choose a constant classic style or are reshaping your look, we have you covered. Link in the description. Run. Time for even more optimal optimizations. Device placement refers to where a tensor or computation physically resides, whether on your CPU, GPU, or another specialized device. This distinction is critical for performance because different devices have unique strengths. CPUs excel at general-purpose tasks. GPUs are optimized for parallel computations, making them essential for training very large neural networks. TPUs are specialized for tensor operations, offering incredible speed for deep learning workloads. TensorFlow, by default, chooses the best available device for your tensors and operations, so you do not always need to specify. However, in certain cases, such as benchmarking, debugging, or controlling resource allocation, you may want to explicitly define which device to use. Demonstration. First, we place a tensor on the CPU, the default device for most environments. Run. If a GPU is available, we can place a tensor on the GPU instead. TensorFlow lists available GPUs, and we use this information to specify placement. Run. Device control confirmed. Enough talk. Let us put our knowledge of tensors into practice by building actual neural networks. TensorFlow provides a high-level API called Keras that offers 3 powerful approaches to building models: the Sequential API, the Functional API, and subclassing the model class. Each approach has its own strengths and ideal use cases. First, the Sequential API, the most straightforward way to build neural networks. It allows you to stack layers one after another, perfect for simple feed-forward networks. In our example, we create a 2-layer network, a hidden layer with 64 neurons using ReLU activation, an output layer with 10 neurons using softmax for multi-class classification. Next, the Functional API offers greater flexibility. It lets you define explicit connections between layers, ideal for complex architectures like multi-input models or models with shared layers. Our example shows how to define an input layer connected to a dense layer of 64 neurons, create an output layer for classification. Finally, model subclassing provides maximum control, perfect for research and advanced architectures, allows you to customize every aspect of your model. In our implementation, we define layers in the initialization. The call method specifies exactly how data flows through the network. On to training. First, we need training data for the model to learn from. In this demonstration, we will generate synthetic data, randomly generated data with a structured relationship between inputs and labels. In other words, known patterns. While this is simpler than real-world data, it is perfect for understanding how training works. Our input data has 784 features. This might be a flattened image, for example. We create labels using a predefined relationship, ensuring there is a clear pattern for our model to learn. Now, let us look at the 3 key steps of training. Step 1. Model compilation. When we compile our model, we define how it will learn. We need 3 components. An optimizer. We are using Atom, which efficiently adjusts the model's parameters. A loss function, categorical cross-entropy in our case, which measures how well our predictions match the actual labels. Performance metrics, such as precision and accuracy, giving us an intuitive way to track progress. Step 2. The training process. Our model architecture includes 2 hidden layers with 256 and 128 neurons. Each layer is followed by dropout, a technique that helps prevent overfitting. During training, the model processes data in multiple passes called epochs. Each epoch is broken down into smaller batches for efficient processing. We also validate on unseen data to ensure the model is learning effectively. Step 3. Training optimization. We have added several automatic optimization features through callbacks. Model checkpoint saves our best performing model. Early stopping prevents unnecessary training when progress plateaus. Reduce LR on plateau fine-tunes our learning rate as needed. While our example trains quickly due to its small size, real-world models often train for much longer on much larger datasets. Remember that every great model starts with a single tensor. Whether you are predicting stock prices, recognizing images of cats wearing hats, or calculating the probability of rain on Mars, TensorFlow is the toolkit that turns your mathematical musings into computational reality. Go, go, TensorFlow!